old school.
It's fine.
What do you mean
It's a personal choice.
No, I get that, but like, you.
Alright.
Are you checking your stuff?
Okay, what?
Thank you. Are you checking our papers?
Sure. I wouldn't run any, man. I would.
You should come down and check your papers.
I'm gonna take
I feel like it's not.
You already did.
You took some of them. I am back tomorrow. Okay, hey, what we're doing today, we're learning how to take derivatives of certain specific types of functions today, which is different than what we've been learning. We've been learning like generic formulas about how to take derivatives of anything. Well, there's certain functions in this world that have a very specific type of answer. That's what we need to discuss today. Once we're through it, we're going to do a bunch of examples of functions and taking derivatives of them. So hopefully you feel comfortable with them. I'll pick a couple out of the book from certain pages. And then they might even be homework problems to given to you. So you might want to pay attention and write some examples down in your notes.
Homework.
But once we do this, we are going to get homework today. Because I did promise you are getting homework today. I didn't want to give you to you Friday.
You don't have to keep up that promise.
So no, it's the promise I'm going to hold up.
Okay.
All right, so here we go. The section we're in. Okay, we're in section 3.3. We're still dealing with the product rule and the quotient rule. But okay. Yeah, let's stop talking, please. Okay. First and foremost here, we need to be able to find the derivative for the following things today. So I'm going to just a quick recap of the formulas we had. You need to be able to do a power rule. Okay, do a power rule to any specific type of function. So if I gave you something like this, and this is my function, we have to be able to find the first derivative of it, because the rule is you drop the power out front, and you subtract 1 off of it. Okay, 1 off the power. This is the first derivative. It's what you'd get if you actually did the limit formula. This will turn out to be 12x squared. Okay, that's what we talked about. You can do this even if they're added or subtracted together. So if you had a bunch of things added or subtracted out back, like this, you could still find the derivative of all those items separately. You would just keep going down the row and doing the exact same process, dropping the power up front, subtracting 1 off of it, and it would just keep continuing on and on and on. And no, you would not have to write all that stuff. A lot of you can do that in your head. But just know that in the back, if you ever have to take a derivative of a number, it just turns out to be 0, constant 0. And that's why this problem would turn out to be 4x minus 5. And yeah, it'd be a minus 5 because x would actually be x to the 0, which would go away. Okay. Are we good with how to do the power rule? Do we feel comfortable with that? We did that a lot last week. That was like the beginning of the week last week.
Feeling good, Ward.
Good. That was, I think, Monday through Wednesday.
Yes.
Thursday and Friday, we talked about how to do the quotient rule and the product rule. So that's where you actually multiply things together. So, product rule. Okay, here we go. Product rule. 5x plus 10 times, let's go 4x to the 7. All right. So let's say that this is my.
She had to leave for a second. She's fine.
Okay, fair enough. All right. Now. Okay, so what we have to do is we have to find the first derivative using this problem. So here's how the derivative works.
No, wait, I got it. 5.
Okay. So derivative of the first.
Come on, dude.
So-
Let me do it.
So it's the derivative of the first times the second.
I have
The full like second function, whatever that is, and again, this is the first, this is the second. That's how I think of it. It's always what word they're written in. Plus the derivative of the second. Yeah, I know I'm using kind of weird notation here. Derivative of the second times the first. Okay. All right. This is kind of the overall goal when you're actually doing the product rule. You have to separate them with a plus sign. Things are being multiplied together. So walk me through it. What do you get?
5
Times.
4. No. Oh yeah, times again. 4x plus 7
Good.
plus. Okay, wait, let me do the math. 24x is 6. Did I do that math right?
28.
What?
4 times 7 is 28. You said 28.
Why was I doing 6 times 4? Okay, yeah, 28 times x to the 6.
Okay, times?
5x plus 10.
5x plus 10. Alright, good. And then you can.
I looked way smarter if you would have let me do it before you wrote the
What's
formula.
128 times 42? 5,376.
Alright. Okay. Alright. It was something, it was an inside joke. Alright, now, at that point, on that type of problem, I'd want you to simplify, go down, add like terms, and do all the good stuff, okay? Just make sure that you're actually taking your time to write that all down. Okay,
Yes.
alright, that's the product rule. Now, quotient rule. Okay, quotient rule, this is one of the final rules, and then we'll get to the specific ones. Okay, good.
What?
So, well, that's the one, that way we can go through it.
It's
All
the
right.
same thing over g of x squared.
Okay, close, it has subtraction.
Yeah, that's what I meant.
Watch your boundaries, Nicole.
So for that one, you said you're supposed to keep going with it.
Yeah, you have to simplify and get to like terms. Yep. Alright, so, let's do the quotient rule here. Let's say that, whatever this thing is, let's say, I'll just use those two as my example. 5x plus 10, and we're gonna divide by a 4x to the 7. Okay, so we got two things being divided. We're gonna try to actually figure out the quotient rule and do this. So, I'm gonna write down the formula, then we'll go through it. And again, the book would ask you to try to keep going. I'll do the same thing, because the problems I'm gonna provide you will not be very big. They're gonna be kind of like this, where they just want you to get used to the rule today. First one, you have to take the derivative of the first times the second. Then you subtract the derivative of the second times the first. So it looks a lot like what we just did with the product rule, but there's subtraction in it. And then you have to divide by the second, I guess, which is the bottom, the denominator, but the second item, that's what I'm calling it. I'm calling it a second. And you're going to have to square it. So that's why the bottom actually gets bigger as you take the second derivative. So the top is getting smaller, the bottom is getting larger. So this is kind of the idea. And again, how I name this is the first, this is the second. I know some books call it numerator denominator for like when they do the formula, they'll actually have it listed out like that.
Sure.
I just think of it like, I want to keep it looking like the product rule. So that's why I label it like that. Okay, now, derivative of the first.
I don't like how it's over the second.
Yeah.
Yeah.
Alright,
Bothers you?
yeah.
Okay.
5.
5
Okay, 5 times.
times 4x to the 7
Good, keep going.
minus 28x to the 6 times 5x plus 10
Good, 5x plus 10.
over
All over.
4x.
4x to 7 squared. Now, when you square the denominator, that's going to actually turn out to be 16x to the 14th, because you'd have to square everything. Yep. Algebra 2.
Oh.
Should have been the first. Maybe even algebra 1. I remember doing some.
I didn't take algebra 1 since like 8th grade, so I don't know how to do that.
Okay. All right. Questions at all about what we did here?
Wait, when we do the answer, do we have to distribute the 28x's and exclude the 5x?
Yeah. They want you to figure out the top, simplify it, and figure out the bottom, and then just leave it.
Yeah.
I give you pretty easy ones. I didn't like really pick like super big, long.
I wasn't sure if we could leave it like that.
Yeah. And the reason why we're doing this is that we need to learn 2 different derivatives today, and that's why we're learning this product rule and quotient rule, because you can't actually like multiply everything through. So.
Sure. Do you want to divide by the bottom thing too, or just leave it when you?
When you get to this, like whatever that 16 next to the 20 or 14,
After you distribute everything?
Yeah, after you do all the top, and leave that on the bottom. That's all I care. You don't need to do long division or anything like that.
What's 5x?
Okay. All right. Okay. All right. Let's go through and let's do the new rules today. We have two specific derivatives we have to find today. So we're gonna do specific derivatives.
Wait. Like.
So like when you take a derivative,
You multiplying and dividing it.
no, when you take a derivative of a certain thing, it has a certain answer to it.
It's kind of like special triangles.
Yeah, like special triangles where like you can find like a set answer for this derivative. It's like you're taking a derivative of this function and it looks like this, and the answer is automatically this answer, like every single time. Okay, Hey, does everyone have my examples written on the board though?
Yes.
Okay, eventually I'll mix these in, like these two, I'll mix these in with what we're doing right now, so you get a feel, and then I'll pick a couple out of the book. So I'm giving you problems that look exactly like your homework, but
Oh, wait.
the two that we're doing, I'm gonna try to explain the best I can, like how they come up with it. So a lot of this stuff is kind of overkill, but it's not like what we did on Thursday and Friday last week.
Was that
That-
too much overkill?
That was kind of beyond what you guys
Do we
need.
do
Wait,
that?
wait, can you
before
not
this
do the
class?
formulas yet? You can do like the numbers, but not like the actual black.
Mr. Ward,
Or
Don't erase the black, but you can erase the red and green and
Oh,
blue.
okay. Alright, I might just go over there then.
Ooh, switching it up.
did we get to the level that we did last week soon?
Yes.
Or is that not something?
No, we're gonna get to that again.
Is that one of the more challenging topics in this class?
That one was.
I am literally the exact opposite.
Alright.
I will put this on my desk.
Okay, so what we have to learn is we have to do the derivative of two specific functions to culture around. So, okay, this is the first one. We gotta find the derivative of e to the x. So e to the x is special, the variable is actually in the power. Now we're gonna come back to this one eventually at a later time. This one's gonna use what we call a chain rule later on. That's another property. Like we have the power rule, the quotient rule, the product rule. There's a chain rule coming up. But this one specifically is our first attempt at looking at it, and it's kind of mixing what we're gonna be in the homework. Anytime you take the derivative, I'm just giving you the shortcut right away so you can see this. When you take the first derivative of e to the x, like the first derivative of that thing, you're just gonna get e to the x. You get it just right back again. So in the middle of a problem, you could be doing, 5 e to the x, and you're taking, maybe this is my example, and this is my function, whatever we're doing, and you're taking the derivative. Well, that's a product rule, because these two things are being multiplied together. So you'd have to go derivative of the 5, right? So we'll figure out the derivative of that function, the first, times the second, plus the derivative of e to the x. I'm doing shorthand so you can see this. Derivative of the second times the first, right? This is where, this is why I said, when we see these very specific functions, these things we're going to be using in the middle of our product rule and quotient rules. So derivative of 5 is 0, so we're taking 0 times e to the x, plus, well, what's the derivative of e to the x again?
E to the x.
Yeah, it's just e to the x, and we're taking that times 5. So your answer turns out to be exactly the same thing you started with.
Why is the 5?
Will that always happen?
What's it?
Anytime you take a derivative of constant, the reason why 5 turns out to be 0 is because technically it has x to the 0 on it, because there's no variable. So you drop the 0 out front, and then you subtract 1 off the power. Even though I know the power would be x to the negative 1, you still have the 0. 0 times anything is still 0. Okay, questions at all? Sorry, you're looking. Okay, that's e to the x. Now, the whole reason why that works is because there's this really long, complicated thing, and again, I don't want to go crazy in depth into it, but how they actually prove that it turns out to be the same exact thing again is because they do this. Now, I'm just going to abbreviate really fast. I'm not going to do the
I thought we were
4.
done with those.
I'm not going to do the 4 pages of what the book did. So, what they do is they do the normal thing where they go, okay, e to the x plus h minus the original function over h, right? So that's the normal limit formula. And the shortcut that, the book doesn't do this, but they do this whole process where they set up tables and they show what the numbers are turning into. You can factor out an e to the x out of the top. And the reason why you're allowed to do this, do you agree that these things are being added together, this power?
I agree.
Powers are added when you have the same bases of things being multiplied together. So if it's x squared times x to the third, right? When you actually multiply those together, you add the powers to make 5. Well, that's what they're doing here. They're taking something with the same base and multiplying them together. So this is e to the x times e to the h. Written like that. This is the same problem, just written differently. This is the shortcut that the book does not show. They try to avoid this. So you can separate, and then you can factor out an e to the x out of the top, where it's like this, because they have a common factor, where you factor out e to the x, and e to the x actually goes all the way to the outside because that's a simple number. It doesn't have an h that you're going to plug an h into it. So it literally separates itself. Since there's no h to plug in, it'll stay the same the whole time. And that'll be multiplied on the outside. And this thing, now this again, this is like a crazy shortcut that the book doesn't show you. This thing right here turns out to be 1. Like when you actually plug in really small numbers, like really numbers approaching 0, and you actually plug them into this thing, and you actually try to figure out the limit, it actually turns out to be 1. Like that's what you get when you plug in very, very small numbers close to 0. So if this whole thing is a 1, what's 1 times e to the x? E to the x. And this is the reason why, like that's like the super abbreviated version of what the book does. Okay? So anytime you take a derivative of e to the x, it turns out to be e to the x. Okay? Alright. Alright, are we good with that?
Yeah.
Now,
Sure.
the next one is not so simple. This one, I'm going to show you it, I'll do an example of it, and then what we have to do is we have to talk about like where did it come from, and that is not the simple part. That's the part that's kind of, it's almost painful to kind of go through.
Would you think that we'll understand it on like the 18th time?
You'll understand like the example, the shortcut that I give you, because I'm just going to give you the formula right away, but doing the actual math is kind of, it's tough.
So,
Okay, does everyone understand e to the x?
It equals e to the x.
Okay, when you take the first derivative. Yep. Okay, next one. In fact, let's leave that. I like that. Let's leave that one there. It's kind of nice to have these just written down. All right, next one. My function is a to the x, not e. E is like the natural number, like
It ends up being
2.7.
the same thing.
What?
It ends up being the same.
No, it's not.
The
And so
opposite.
this applies to anything that's not an e. So like this could be, you know, a can be any number. It could be 7 to the x power. Could be 8 to the x power, 2 to the x power.
8,000.
Whatever they
The
are.
variable was just an e, it wasn't
Yeah, so-
necessarily the natural number, it was just a variable e.
Yeah, so this is like the natural number.
Yeah, but what if it was just a variable that was e, not the natural number?
If it was just a regular variable, you would follow this rule then.
He
Okay,
doesn't understand what you're saying.
yeah.
Alright,
I know,
I said it would follow that rule.
Yeah, okay, I
Alright.
get it. Yeah.
Now, figure out the first derivative. Here's the shortcut you need to know. And then we'll kind of go through like the process. I'll do an example of it. Okay, the first derivative will be the natural log of whatever the base is. It's the natural log of whatever the base happens to be. And then it's times a to the x. So it's very, very similar to e to the x. In fact, that rule actually explains why e to the x actually works out the way that it does. Is because the e to the x would almost follow that same rule, but it would use the shortcuts for natural logs. So I'm going to show you, like using e, that it would follow the same like sort of rule, but it looks differently in like the answer.
So what'd you say A was again?
A can be any number you want. So it can be like a decimal, it can be a number, it can be a fraction, it can be anything you
So,
want,
like, if
as
you
long as it's a number.
7 to the x power, and you want to find the derivative of that?
Exactly. So yeah, so
Like-
let's just do that example then.
Okay,
Okay.
It could be anything except that. What number does
Or, I go check on it.
16.
She's sick?
16, 50, 100.
Let's make sure she's okay. Alright. Alright. Good. We got plenty of time. Alright. So, let's plug in a 7 like we were saying. Alright. So 7. So, my function, I'm going to call it g. Let's call it 7 to the x. Okay, 7 to the x. So, my first derivative of this thing, so g to the g prime of x, is going to be the natural log of 7, right, because it's the number, whatever the base is, times 7x. And this number's in the parenthesis, that's the number you take the natural log of, and the 7x is just like the number in the back, right? Or you can put the 7x out front. That's the derivative. It's pretty easy. That could be any number, it could be a decimal, it could be a fraction, whatever, it could be a negative, I don't really care. Whatever you're doing, when you take a derivative with the power up like that, that's the rule. Now, what I warned you of earlier is that there's this thing called a chain rule that's going to come up later. If they start putting numbers up in here with the x, if they start putting numbers on the inside, now the answer's completely changed.
What do you mean numbers on that?
Like if they, instead of saying like 7 to the x, if they say 7 to like the 3x,
Okay.
that's a different
I didn't know
problem.
if you meant like
This,
that or like
no,
something to the-
it has to be a 1x in the power for this rule to work. So otherwise it follows the second rule, which is called the chain rule.
Sounds like something to try to trick us on this.
No, it's just something that we need to be aware of, because we're gonna see the chain rule later and I'll try to give you
You
similar
gonna show us
examples.
today or?
No, not today. Chain rule is like later this week.
It's
It might
way
be
too
as early as tomorrow or Wednesday.
As early as that?
It's early.
Well, I
So-
bet we don't learn it on Wednesday.
so- Oh, yeah. Tomorrow, I might have to do it tomorrow then. I might have to show it.
We might have to just go for next
Alright.
Monday.
Now, hey, let's talk about why. Hey, let's talk about why this rule actually does work for this one. Like, even though I know I said E is like its own power, it's like its own number.
Well, because L and a B would cancel out.
Exactly. So, if you're to take the natural log of e to the x, like you're taking the natural log of whatever the base is, right? The natural log of the base number times e to the x. Nicole's absolutely right. Like this is the first derivative. Like if we're following that same rule over there. And the idea is that this part right here actually does make the number 1. Because the base, the natural log, the base is actually an e. So what you're actually doing is you're trying to figure out what power do you put on an e that would make e. Well, that'd be the power of
7.
1,
I literally have
right?
never
So that'd be a
understood what
1
that means.
times e to the
It's a
x.
natural number. It's
And so that's the idea.
2.7.
What is E? It's like,
E is 2.7. It's the growth.
I knew it was
It's
something
the
like
growth of like bacteria and populations like over a long period of time. What that number actually comes from,
all.
the natural number E, it comes up in the power rules for compound interest when you do a problem like this.
Do you think the cavemen discovered compound interest?
Now, it's when you do a problem like that, where you can plug in numbers and the numbers get bigger and bigger and bigger. And this is like compound interest formula for like student loans and home loans, mortgages and stuff. As the number, as h gets bigger and bigger and bigger, it would eventually, like this answer turns out to be e. Like this thing would just approach e, and then you take that times whatever your principal amount is, like how much you're borrowing. So,
What?
if your numbers get bigger and bigger and bigger. So,
What do you mean?
like when you plug in like 1,000 or you plug in 1 million in here and you put that and you go 1 over 1 million, right?
No, you said 1,000, I thought.
So,
He changed
1,000,
it.
a million, you go bigger and bigger and bigger.
Can I get you
So,
2.7?
This would give you, this would be
Put a
roughly
couple in there.
2.71 blah 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 blah.
Hey
as you go
Josh,
bigger
instead
and
of
bigger.
managing, instead
It
of
appro- it
memorizing pi, we should
approximates-
memorize.
It approximates the natural number.
Can you put Steve Jobs in
Okay. Good.
Yeah.
Can you
Okay. All right. Now, obviously this is like, I'm just kind of dropping these both on you, but I want to make sure that you understand how to use them in a problem. So I'm just going to pick a couple of homework examples for us that would use like this natural number, or it uses E, and we'll put them in like quotient rules and product rules and stuff like that, okay? So let's do an example or two of that, so you can kind of see one. So, let me just pick one out of the book and we'll try this out and we'll see if this makes sense where we're using these basic rules. So I'm just gonna pick a couple right out of the book. These could be easy homework problems for you.
It looks pretty.
Pick one I have. Yeah. All right, so here's the first one.
Will you tell me what number it is?
It's number 10.
18.7.
Thank you. On what page?
There we go.
139. Okay, so this is number 10,
Do you have this book memorized
Can
yet?
you see this?
page 139.
Will you soon?
Yeah, eventually, but give me a year or two. I'll have it mostly.
I can
Alright.
do J's.
So, 25x squared
Can you
over
put
e to
page
the x.
139, number 10?
And this is my function on number 10. I don't care what the g of x thing is. And what they want us to find is the first derivative. Okay, so finding the first derivative on this thing, obviously you can tell like we're using an e to the x. So like it's in the middle of a problem, even though this is just a simple like quotient rule, they want you to understand that in the middle of this thing we'll have to do the first derivative of e to the x. So doing this part, we're taking the derivative of the top, which is 50x, times the bottom, that's the second. We're going to subtract the derivative of the bottom, times the top. And yes, I'm doing this on the fly, all over the bottom squared. And this is how you actually write e to the x squared. You actually put a 2 there. That'd be the final answer. That's the first derivative of that thing. Now again, I know I went really fast, sorry. The derivative of the top is you drop the power of 2 out front, 2 times 25 is 50. You cut 1 off the power, so it's x. Times the bottom, minus the derivative of the bottom. Well, derivative of the bottom is just e to the x, I warned you of that earlier. Times the bottom, or times the top, sorry, all over the bottom square.
You don't expect us to like simplify this or anything?
Well, that, yeah, you can simplify that. You can see if it actually works out. You shouldn't be able to actually subtract the top because the top will have different variables for x's. It'll have x squared versus x. You can't actually subtract.
So we just
So
leave
why
it
is
that
it
and
like
turn
this?
it in?
This
What?
is the answer?
That's basically the answer.
Basically.
Yeah, well, I mean, the only thing you'll have to do is multiply through. So you'll have to write 50x e to the x minus
How do you write
25x squared e to the x. That's just what I
Why is it e to the 2x?
We squared the bottom.
Wait, so
When you square the bottom, I'm just putting a 2 on.
Yeah.
How do you write the 15?
2x, not x squared.
Yeah, well, it's e to the x squared, and you just multiply the powers. Because that's a product rule. That's a power rule in algebra 2 or pre-calc. When you did this, when we did that, when we squared the bottom,
It's just an x, that's all.
yeah. When you have a power on power, you just multiply these together.
Oh, okay.
Yeah, sorry, I was kind of doing it on the fly.
Yeah, that was kind of.
It's okay.
Wait, how do you write the
Will you come here and
15?
look at this?
How do you write the 50?
I don't understand if I did it right.
50x e to the x. Just put an extra jump.
Does it matter what order it goes in? I prefer to do E.
No. You can do e, that's fine. 50 e to the x, x.
And then 25 E to the X, X squared all over E over 2X. Or E to the 2X, whatever.
Okay, alright. We're good with the first example. Yeah. Okay. Second one.
What number? Don't plug it in.
This is gonna be a.
Okay.
This is a little might be a little slower.
Okay. Alright, this is number 6 on page 135.
What did he say?
Page
6 on 135.
Number 6, page 135. And here's my function. I don't care what the name of it is. I'll call it g of x. It really doesn't matter. Good call. Okay, 2 to the x plus 2 times 3 to the x.
What?
Okay, so now why I picked this one, it had one of the numbers. I could have put one as easy as just putting an e to the x in there. But the reason why is that we're going to go through the normal derivative, but at some point in that back, because remember, these are just being added or subtracted together.
Yeah.
So you're just doing your normal addition or subtraction rule where you just take derivative of each one as you go. But back here, this is a product rule.
Really?
It's a product rule because two things are being multiplied together. So I know that in the middle of this problem, you'll have a product rule. One of the terms will cancel out, the other one won't. And so we'll find our final answer. So as we go through, we're going to figure out the first derivative. Okay, you're just going to go piece by piece through there, and these will be separated by a plus sign, right, when I do the derivatives. So derivative of 2 to the x, what we just talked about a little bit ago.
1, 2, 17.
When you take something with an x in the power.
2 to the x.
You gotta multiply. Natural log of 2 times 2
Natural log of
There you go. Natural log of 2
Oh, I was
times
thinking of the other one. The
2 to the x.
I was thinking of the e.
No, not the e. Okay, when it's a number, it's the natural log of the number times 2x now. Okay. The 2 is in parentheses here. The 2x is not with it. Now, if you want to put the 2x out front, write 2 to the x, natural log of 2, that's fine.
That's not gonna work.
Okay. Alright, so now, in the back, now we're doing a product rule back here. So this one, because they are being multiplied, and I can't actually just say that's 6 to the x, you can't do that. They're not the same bases, you're not allowed to multiply them together. So, we have to do a product rule. Derivative of the first times the second plus derivative of the second. Derivative of the second times the first. Because the derivative of the second item, when I do the derivative of the first times the second, the derivative of the second item is natural log of 3, natural log of the base, times 3 to the x, times the first item, which is the 2 that's out front.
When are we ever going to use this like outside of high school?
Never.
This is for engineering level, this is for business interpretation, this is for anytime you're looking at slope rates of changes on really complex curves.
So how So what computer
Me?
program does this for us?
Hi.
Your calculator.
Let's make them a.
My calculator doesn't.
But this would be looking at a sales growth, like where there's a sales margin, and trying to fit that curve to like your
Do
actual
you use
profit.
this on your farm? Is there a first derivative button? That's what I thought.
Shroot.
What?
Is there a first derivative button?
Oh, is there? Shroot bed back.
Certain calculators do have that.
Do they really?
That's kind of
That's kind of
cool.
cool. actually.
Mr. Ward, I have something.
What
for
about
you.
any of our calculators that aren't, if we don't have a graph?
Is
Alright.
yours, Mr.
Now-
Ward? Did your nice one in college?
What happens to this item right here?
Zero. Cancel.
This is 0. Now, most people get to figure out
More, the blue one.
when you're doing the product rule and you have a constant, some people just know that they can just erase that term and just go after the second one. Like some people get so good at that, where it's like, okay, I know that this thing, the first derivative of the 2 will be 0. I'm not even gonna do that first part of the parentheses, I'm gonna do the second half. I always personally write it out so I know which one I'm doing. I'm doing the derivative of the first times second, derivative of the second times the first. I like to write it out so I know for a fact where did it go. Because if I subtract, maybe I did the wrong things. Maybe I did the wrong multiplication.
Yes, honey.
Okay? And then this would be, this is kind of like the answer I'm looking for in the very end. You know, the 0 would obviously go away. Eventually, you can rearrange this thing in any form that you like. But this is how I'd probably write it.
Put it in standard.
No, it's not an equation, it's an expression in simple way.
What forms are there then?
This is just an expression, there's not a form for an expression.
Wait,
You can put
so
it in descending order if you
Didn't you
want.
just say you can put it in any form?
Yeah, you just said we could put it in whatever form we want.
What about Y and Z?
Whatever order you like.
Oh.
Sorry.
I really don't understand why we put the ln in this.
No.
It's just-
Is there any way you could explain why we're doing that?
Why the natural log
A
comes
to
into
the
play?
X rule.
Oh, I looked
Yeah,
at that,
it's
but
the A to the X rule where it comes up.
that itself doesn't make sense to me.
Okay, like where did it come up originally? Okay.
I was born at night without
Otherwise, you wouldn't get a state champ.
Okay, here's the question I got. Hey, this is an honest question. Where did the natural log thing come from? Like, why when you take it like a natural log of a to the x, does the natural log have to be natural log of a times a to the x? Like, why did that come out about?
Aren't you the
Because
one
you
that's
said
supposed to
so.
know that?
Yes.
Because
So,
you said so.
It was a teacher question, it wasn't a real question.
Dress asked me. You want to know where it came from?
Yeah, I don't get it.
Because you said so.
So why did you ask us?
But teacher
I'm rephrasing
questions,
the question. So in case I'm here.
teacher questions are when
Now.
teachers ask questions they already know the answers to.
So, it's called
So like a
rhetorical.
rhetorical
Yeah.
question? There's
See if
actually a
you
word
know.
for that.
Hey, here's the idea. You'd factor out a to the x here, just like we did earlier. A to the x times a to the h minus a to the x all over h. This is like what I did earlier. This is still limits out front. This is the limit as h approaches 0. So you'd factor out a to the x. This a to the x would go out front of the limit. So I'm going to multiply at some point by a to the x. You guys get the idea, like this can drop out front because I can factor it out. And so what you're left with is a to the h minus 1 over h as the limit as h approaches 0. And the idea is that this is an e.
You have to write the A to the X, right?
Okay. Oh wait, a to the x up front. All right. This is an e, so it's not going to turn out to be 1. It's going to turn out to be whatever this base number basically is. To the natural log of it, and the reason being is that here's how they, and this is really tough, like generic ways of writing this. They separate. I hate writing this. Oh god, this is gonna get ugly. A.
Do you believe in a pony for every American?
All right. So, hey, I'm just trying to explain like where that thing came from. So here's what they're gonna do. Shh. They're gonna separate the A and the H like that, and the minus 1 over H, right? And it still has the limit and all that stuff out front. All right. But instead of an A, they write it like this: e to the natural log of A. Now I'll explain why here in a second. Is because when you write something like that and the limit's still written out front and that A of x is still out front, when they write it like that, e and the natural log actually cancel each other out. It's one of those rules of natural logs and logarithms that it's one of the rules that these would actually cancel and you'd be left with A, so it's the same answer.
Yes.
And this would actually be multiplied into it. And then what they do is they take out, so natural log of A times H. And what they do is they substitute a different letter in there. And why they substitute a different letter is they don't like looking at the natural log sitting there. So they substitute a T in there. And what they do is they solve for H, because this problem has H's in it. So when they solve for H, this is T divided by natural log of A equals H. And so once they solve, they plug that in to this monstrosity that's up here. That this thing multiplies together and turns into this thing where
What is happening?
I think those,
Where
number signs.
these things multiply together. They substitute the T in. They substitute the T in for this thing right here, because T is natural log of A times H. So this turns out to be a T. So the reason why they did that is now they have an E sitting there, and that's a number we can actually take a natural log of, or take the limit of. And this H now became T over natural log of A. And so what happens here is that when you have a fraction on the bottom, you can actually multiply it by the reciprocal. And so the reciprocal will push the natural log of A out front with the limit as t approaches 0, and that a to the x is still out front. This natural log is just a number. It can join out front. And this is something we just talked about a little bit ago, is that when you take, and you're taking the limit, when you're taking the limit of this thing right here.
That was a negative.
What?
It was a negative before. But you had a to the x minus that. Never mind, just keep doing math. No, just do math.
Okay, when I take the natural log, or when I take the limit as t approaches 0, this thing right here was actually approaching the number 1.
I like how you did that so you didn't have to rewrite the.
Yeah.
Is this like the weirdest?
What you're seeing there, Darcy, is how they came up with the natural log idea, is they changed the A problem into an E problem, like a natural number problem. And when they did that, when they actually tried to change the variable, change the base, it kicked a natural log out front because of the change in variable. And so it's one of those like super, like when you see it, you're like, okay, that somewhat makes sense. But unless you see it for the first time, like it's kind of difficult. Unless you actually know like all the math that's behind it. Like just showing that is painful because everyone's like, oh, you get it. I do
We
not.
have 2 minutes and you say the homework?
Okay. We'll get on with tomorrow.
Oh, great.
He's like, Mr. Ward, you broke your promise. You did promise me that homework. What do you do? Not growing up.
You weren't my class.
Quotient Rule?
Okay. What does that say?
Are you gonna no? Why did I get ready?
We reviewed a lot just for to ensure that. And then we did the product rule.
Have other people in there?
All the things
I think that it's also for days and everything. Yeah, of course. I like it.
I missed this activity.
Oh, that was my arm. Can you see? Oh, you can see it. Oh, that's cool. Mr. Ward, come look at this. Are you looking?
You guys did.
Yeah, that's cool.
That is cool.